Hello Year 10. I thought it would be worthwhile just going over the ultrasound and echoes quiz that you did for homework this week, just to highlight a few little bits and pieces that people got wrong and hopefully help you so that you can understand going forward. So hopefully on your screen you can see the quiz, and we've got sound waves and ultrasound are both, and you should click longitudinal waves because they are longitudinal waves. Light electromagnetic spectrum is a transverse wave. Okay, now here we have, it tells us that two different instruments are used to create the traces shown where the musician's playing the same note. When we look at them, we can see that the frequency is the same for each of them because on our oscilloscope traces, the x-axis is time. And you can see that the time taken for each waveform is exactly the same. So we need to click yes because the frequencies are the same. The different shape is just because they're on a different material, different instrument, sorry. Right, a bat emits a squeak, and here's an echo from a wall after 0.2 seconds. How far away is the wall? The speed of sound in air is 340 meters per second. The thing here is not to forget the half. Remember, he emits the squeak, it reaches the wall and reflects back. So in actual fact, to go to the wall, it only took 0.1 of a second. So the wall is 34 meters away. Oh, look, I'm rising up here. We're doing well. Okay. Which of these give answers in the ultrasound region? There may be more than one correct answer. Now, what you would have to do for this question is to work out the frequency of each of the answers. And I'm just moving it so that I can see my calculations. What you would find is that a wave speed with 330 meters per second and a wavelength of 0.015 meters will give an answer which is higher than 20,000 hertz, so it's in the ultrasound region. And the other option is a wave speed with 1500 meters per second and 0.03 meters wavelength. Now, I'm going to try and do something quickly here to show you how you do that calculation. So bear with me. Let's see if we can do this. Okay, so here we have the question. And what I'm going to do is I'm going to scan in these questions and answers so that you've got the full mark scheme and you can correct or use them to practice going forward. But we have the wave speed equation here, v equals f lambda, and you need to rearrange that to find the frequency. So we need to divide through by lambda in order to isolate f, the frequency on its own, and we end up with v divided by lambda. So the wave speed divided by the wavelength. Okay, so that's how you would calculate the frequency. Right, let's go back to the game. And let's submit that, and we've got that right, which is good, really. It's going to be embarrassing if I click the wrong one now, isn't it? Okay, if a sound has a wavelength of 2 meters and a frequency of 165 hertz, what is the wave speed? Well, here we're just doing v equals f lambda. We've got f 2 meters, sorry, f is 165 hertz, lambda's 2 meters, and so our answer is simply the two multiplied together, and that is 330 meters per second. There we go. Right, now, diagram shows how a very high frequency sound can be used to check for internal cracks in a large steel bolt. The oscilloscope trace shows that the bolt does have an internal crack. Which peak, A or B, shows there is a crack? So we've got the initial pulse, transmitted pulse here, reflected from something and then reflected from something else. Now we know we would get a reflection from the end of the steel bolt, which is probably B, which would suggest that A is the crack. I'm sorry, my cat has decided he wishes to talk to you as well. Right, here we go. A loudspeaker produces 6 waves in 0.001 seconds. Can a human hear the sound? So the first thing we've got to work out is what's the frequency of the sound to see if the human can hear it. So let's have another look at my sheet of paper. And what we've got here, we've got the time period of that wave is equal to the time for 6 of them divided by 6. So that's the time for 1. And we get 1.67 times 10 to the minus 5 seconds. That's quite a short time period. But our frequency is defined as 1 divided by the time period. And if we put that into our calculator, we find we end up with 60,000 hertz. So no, we cannot hear the sound, and therefore it is in the ultrasound region. So we're going to type our answer in, no, and submit it. Oh, good, got it right. So here we go. Which of these statements is true? Now I've got an apology here. I had an oops moment doing this. Everybody has them, don't they? So I'm sure you'll forgive me. I should have written sound travels faster, sound travels slower. Okay, so sound travels faster in more dense materials because the particles are closer together. Okay, now we've actually got 2 that say the same thing. So hopefully I chose the right one. If you got that one wrong, I'll spot it and give you an extra mark. Okay. If a sound from a bass guitar has a frequency of 110 hertz, what is the wavelength? And we're given the speed of sound. I've been really nice to you so far. I've not done any nasty units here, conversions and things like that. So we've got a bass guitar, frequency of 110 hertz. We know the speed of sound is 330 meters per second. We've got to use V equals F lambda, and again, rearranging it, but this time our wavelength is equal to the wave speed divided by the frequency, and we end up with 3 meters. Right, next question. Calculate the distance in meters to the floor in the bolt that produced peak A. The speed of the ultrasound was 6,000 meters per second in the steel. Now, what I'm going to do is show you my answer to that, because that's not quite so straightforward. So let's have a look at my answer. So here we've got the information. We've got our peak A, and we want to know the distance along the bolt that that floor is. So first of all, we need to know the time taken for the echo. So you have to read all the information you're given, and it tells you that 1 centimetre, which is 1 little square, represents 0.00005 seconds. Now, as soon as you see something written like that in a question, you need to switch on that massive concentration button in your head. That means that you count those zeros really carefully right the way through the question, and when you're writing things down and when you're putting it into your calculator, because that's where errors really occur really simply. So here we know that we can count that it's taken 5 squares for that ultrasound echo to return, and 5 times the time for 1 square gives us 0.00025 seconds. But we have to remember this is an echo process, so the sound has gone to the crack and back, so we must divide it by 2. And so we have our speed, 6,000 meters per second, multiplied by the time just for the ultrasound to go to the crack, and that equals 0.075. So let's put that into the answer, and then hopefully we will get it right. Okay, next question. John stands 170 meters from a cliff and he shouts. He hears an echo. How far does the sound travel in total? So we've got 170 meters and he's shouting. The sound is going to the cliff and back. So it's double 170, which is 340. Okay, captain of a ship is calculating the depth of sea below. He measures the time taken for the ultrasound to return to be 0.6 seconds. And he knows the speed of sound in seawater is 1500 meters per second. His calculation is that the depth of sea is 900 meters. Is he correct? And why? So, I can't find my working for this one. There we go. So the answer is no. And how do we know it's no? Well, we know that speed is distance divided by time. He's got the time to return as 0.6. Now we know that that's double the time taken to get to the seabed. So it should actually, we should use 0.3 seconds. And we know that the speed is 1500 meters. And we know that distance is speed times time. So 1500 times 0.3 is that 900 meters? And the answer is no. He's forgotten to halve the time the sound travels to and from the seabed. If 5 waves are produced in 0.01 seconds, how many waves are produced in 1 second? So here we know that we've got 5 in 0.01. We just need to multiply through until we get to 1 second, and we have 500 waves because that's 100th of a second. Okay, I'm sorry I can't turn this bit off. Right, how many waves are produced by the loudspeaker in 0.0001 seconds? So the trick here is to count full waves. So to mark on your diagram where the start is, and then you count 1, and then 2, and then 3 full waves in that time. Don't be tricked by the number of peaks or the number of times it passes the equilibrium position. That's often a mistake that's made. What happens to the ultrasound which reaches the boundary between 2 different media and is not reflected? It's transmitted. So it goes through into the next media and then will be reflected from another boundary. A boat using sonar. The depth of the sea at that point is 300 meters. How long will it take for the boat to receive the echo if the speed of sound in water is 1500 meters per second? So what have we got? We know that, oh, that's not the right answer. Here we go. We know it's taken, we've got 300 meters, we know the speed, so we know the time, we can calculate the time for the sound to reach the seabed, which is just distance divided by speed, because time is distance divided by speed. But we need to remember that actually for that echo to come back, we need to double that answer. So we end up with 0.4 seconds. Next one. Which of these would you use ultrasound for? Well, you would use it for scanning a fetus, you would use it for cleaning plaque from teeth, you would use it for treating kidney stones, and you would use it for cleaning jewellery. All of them. Sorry if you only put a couple and then got that one wrong. I was being a bit mean. Right, an observer sees a firework explode 1 kilometre east of him. He hears the sound after 3.1 seconds. When a firework explodes 1 kilometre west of him, he hears the sound after 2.9 seconds. Why are there 2 different times? Well, sound is travelling through the air, but actually the wind can help or hinder that sound to arrive at your ears. So the fact is the wind is blowing, and because the sound to the west, so to his, imagine he's facing north, to the left of him, is coming quicker, so the wind was blowing from the west, okay? So it was making it go faster towards his ears. If a boat is using sonar with a wavelength of 5 centimetres, would it be able to detect a shark of length 3 metres? Yes, it would, because the ultrasound would be reflected from the shark back to the ship. I think this must be our last question. If a ship was using sonar with a wavelength of 5 centimetres, would it be able to detect a small fish of length 3 centimetres? And the answer here is no, because the ultrasound is diffracted around the fish. Now, if you remember diffraction, we looked at it with radio waves, when we're doing the electromagnetic spectrum. The maximum diffraction effect is when you've got a wavelength equivalent to the gap size. So that's why the wavelength of those long wave radio waves diffracts around hills, and houses on the other side of a hill from a transmitter can receive it. But the smaller wavelength TV signal won't diffract around the hills, and the houses won't receive it. Now, in this case, we had the shark, which has a length which is much, much bigger than the wavelength of the ultrasound, and so therefore the ultrasound was reflected. But here, that fish is small, and the size of the fish is roughly the same size as the wavelength of the ultrasound. And so therefore, it's as if the fish isn't there. The ultrasound will diffract around it, and it won't be reflected. It won't detect a reflected signal. So no, you won't detect the fish. Okay, I think that's all of them. I hope that has helped, and if not, do just ask some questions and send an email if anything is unsure still to your teacher. But hopefully that's helped with ultrasound and echoes. Thank you.